you treat it the same way. Who wants to tell me what's good? Who haven't I heard from today? Jean-Baptiste, MJB, hit it.
4/3 x cubed plus 2x squared.
That is the most beautiful thing that has ever come out of your mouth. Wonderful, wonderful, wonderful. 4/3 x cubed plus 2x squared. You guys with me on this?
Yeah.
Not too difficult, right? Easy to get confused when you start doing it a little faster on your own, doing your homework. All right, let's go back to this do now, which I gave you guys a while ago. How are we doing on time? What time is this period over?
2:21.
Oh, please. All right. Raise your hand if you did the do now. Teacher's pets. Put your hands down. The do now says take the derivative of these two functions. Okay. What's the derivative of sine? What's the derivative of cosine? What's the derivative of negative cosine?
Negative.
Sine.
Wait, no, sine.
What was
What's the derivative of anything? Positive or negative?
Negative.
That's a good trick. All right. Anyway. So what's the derivative of sine x plus 5?
It's cosine.
Is it?
Yeah.
Yeah, that's right. What's the derivative of sine x plus 248? Okay, and the reason why this is the case, of course, is because the derivative of 5, the derivative of 248 is what? Right. The derivative of a constant is. Right. So that's why both these functions have the same derivative. You with me on that? Okay? They're the same. Okay, they have the same derivative. Two different functions have the same derivative, okay, which can be a problem, right? When we think about antiderivatives, which one of these functions is the antiderivative of cosine? Is it don't know, neither, or both? Raise your hand if you think it's don't know. Raise your hand if you think it's neither. Raise your hand if you think it's both. Both is an answer. Okay. Like I said before, the definition of an antiderivative is any function whose derivative is the thing that you start with. So these are antiderivatives of cosine because their derivative is cosine. Right? So they both are. Not that important, but semantics is not important. Semantics? Is that important? What are my English people? I don't know. Whatever. The details, the deets. Okay, so you with me on this? Two functions have the same derivative, which means that there's more than one antiderivative of a function, right? So for example, we just had this example a second ago, right? 5x to the fourth. What's its antiderivative?
X to the 5th.
Right, that was the first example from the thing before we answered it. Right, is x to the 5th, okay? But another perfectly fine antiderivative would be what? Somebody make one up right now. X to the 5th plus 2. Okay? Because that's also, you take the derivative of that, you still get 5x to the 4th, right? So there's an infinite set of antiderivatives for any function. Because you can add a constant or subtract a constant all you want. So another example, x to the 5th minus pi is another one. You take the derivative of this, you get 5x to the 4th. These are all antiderivatives. Yeah, I look where you're headed. And that's where we're headed right now. So let's get back to some math about this. And we're going to learn about something called indefinite integrals. Okay? You're getting a lot of vocab all in your face right now. You ready for it? Okay, so same idea that I was just describing graphically. Feel free to write this if you want to draw this graph. I could never draw this graph. Yes?
So, is this a part of the first power?
No, we're moving on. Indefinite integral is a big old topic. But like I said before, calculus has two parts: differential, which is derivatives, and integral, which is about integrals. We're about to start. And it's integral, if you don't understand any calculus. Okay. So take a look at these three functions. What do you think is true about all three of these functions? Somebody raise their hand and give me some kind of astute observation. Yeah, McCormick, you look like you're on the bridge. Do it.
They're all antiderivatives of a function.
Of something else, right?
Yeah.
How do you know?
Because they got the same shape, they're just at different heights. So
Exactly, right? So if you think about what a derivative is, somebody said before, the derivative is a what of another function? The slope. Yeah. So I think it's where you were going towards before. Right? The antiderivative, we don't know what it is yet, but the derivative of a function is its slope, right? So all three of these functions, if you look at a current x value, take this one, for example, notice how they all have the same slope at that value, right? All these functions have the same slope, they have the same derivative. And it comes from this same property I was just discussing before, right? A function's slope is not determined by these constant things, which just shift it up and down. So multiple functions can have the same derivative.
which means there could be multiple antiderivatives for a given function. Whew. It's a lot of thinking. Okay, at each x value, they all have the same slope, right? And it comes from the fact that the derivative of these constants, pi and 2 and all that, are 0. So it just drops out when we take the derivative. Okay, thus, they are all antiderivatives of some mystery function. Right? We said this before. And the idea also is that you could generate this graph, you could shift it up. You could generate this graph, you could shift it up and down as much as you want, a million times, a billion times, a bajillion times, a googolplex, in fact. 10 to 100 times. Okay? And even more than that. The truth of the matter is there's an infinite number of functions, of antiderivatives of a function, right? Because you can always shift it up a little bit more, a little bit less, right? Or however much you want. Okay? Right? Just like we had here before. We saw that a second ago. So, you should write this. I think you should write this. It's up to you. An indefinite integral is like an antiderivative, but it represents all of the antiderivatives that a function can have. So we just said there could be a bajillion of them. It's technical math term, like I said before. I'm going to speak in technical terms. There could be a bajillion antiderivatives. And this thing, this indefinite integral, which I'm about to introduce to you, represents todos. You feel me? I'm not going to move. So that's what the definition of this thing is. Well, it's sort of a definition. If it can even be defined because it's indefinite. It can definitely be defined. An indefinite integral represents the entire set. All those antiderivatives, we're going to do it in one simple equation. All right? So the indefinite integral, and you should definitely write this because look, it's bolded and underlined. Although we've learned in our physics classes in years past that it's not necessarily enough to indicate importance. You guys remember that? Last year on the test there was it was like true, false or something, and if you said it was false, then you had to explain why, and I put that like, if it's false, explain why in bold, underline, and italics, and people still didn't do it. Including Temi, who would have gotten 100 on the test if she didn't do it. So again, the indefinite integral of f of x, its antiderivative is big F of x. But we add this plus c, you see that? Which is just a constant. It could be anything. We don't know what it is. It could be 9 billion. It could be negative pi, as it is here. It could be e. It could be 7. It could be my birthday, except that's not one number. It could be anything. Okay? And because it's general and it can be anything, this equation represents all of the antiderivatives. Got it? What's that? Sort of. So you get this part, right? How these are all antiderivatives of 5x and 4. So you can consider this guy to be x to the fifth plus 0. So all of these are just x to the fifth plus a number, plus negative 5. Right? And so now we're just saying, all right, let's call that c. You don't know what it is. It could be anything. Let's call it c. Is that all right? I. Okay. You might want to just draw a little arrow to the c that you have there and label it. It's called the constant of integration. It has a name. And like I said, it can be anything. And if we want to figure out exactly what it is, if we want to specify one individual antiderivative, then we'll have to figure out what it is. We'll see how to do. Before the week is through. That'll be cool. That's another day, which I have not yet planned. Calculus party? A derivatives party?